Thanks so much. I'm so delighted to be here, particularly to come and see a number of old friends that I haven't seen in quite some time, but also to see what incredible things that you all are doing here. It's been an amazing school for quite some time, but I'm also very excited about some of the new directions you're taking. I'm going to be followed by Anna and Sheila, who, as both researchers, as academics, but also as practitioners, have an incredible body of work to show you, a body of work that puts anything that I have ever done to shame. So I'm going to stay a little bit away from any of my own work. Instead, I want to talk about some of the modes of thoughts, the way that we frame the questions that we ask within this field, particularly of dealing with advanced technologies, particularly in how we deal with knowledge. In my particular area, I work mostly on sort of energy phenomena, but energy phenomena all the way from the picoscale on beyond there. In which case, one of the things I've always been quite fascinated about and talking to different people about how energy behaves, about how heat transfers, about how air moves, is how often there's this assumption that it's intuitive, that we feel heat, we feel how air moves. And I think the provocation I want to put out for you, and actually sort of the premise of everything I do, is that intuition, senses, are really, really false advertisers of what's happening out there. And too much of what we think we observe is what we think we see, colors the way that we think we know how things work. And the reality is that it is a very poor picture into the way that things work. I want to briefly sort of, just in a moment, talk a little bit about where I began in this, because I certainly began in my own doctorate with trying to understand the combination between really advanced tools for simulation coupled with really advanced technologies, how that was going to bring together. And this is the type of work that I have now spent not many years questioning, but wondering why it didn't have traction. So much of the rest of the talk is going to deal with why I think a lot of this original work didn't have traction. And a lot of it has to do with a very pervasive set of beliefs that we have, both about information and about technology. These are images that I was just sort of reminded are in Fried Augenbrau's book that he wrote many years ago, and so you can tell how old these images are. They're images that are familiar now to everybody in architecture of computational fluid dynamics. I will say that these particular studies cannot be done with any tool available in architecture. They're actually simulating at the nanoscale very discrete, almost atomic behavior of air, molecular behavior of air, mostly because my interest was finding this one little moment of transition that takes place between laminar and turbulent flow. The interesting thing about that is if you can manipulate that moment, you can change the heat transfer by a factor of 10. So instead of thinking about a piece of glazing and worrying about making it double glazing, triple glazing, inert gas-filled glazing, if you could just modify the moment, shift the moment at which it becomes turbulent, you can change its heat transfer by a factor of 10. We want to have everything be constituent with the materials we operate with, but it's not the materials themselves, it's actually the context in which they exhibit that drive their behavior, and that's sort of a key realization that we're dealing with. But that was one part of it, and the other part of it was sort of my interest in challenging the technologies that we had for architecture. So if you think about the standard technologies for moving heat, starting with the room size air handler to heat pump, and then down to a thermoelectric device, and all the way down to a heat pipe, what's hard for many people to imagine is that all of these move the same quantity of heat in the same time. And I don't mean relative to each other, I mean absolutely. The tiny heat pipe is moving just as much heat per hour as does the large air handler. The only difference is that these devices are doing so efficiently, whereas the devices that we typically use on buildings, the ones on the left, do so through the most inefficient means known to humanity. And yet those are the ones that privilege the way that we deal with our building systems, because we have very few means of actually sort of like operating directly. And again, that's what that research was about. And even more so, my research was very much about starting to take advantage of even more micro devices in order to make those tiny changes. So sort of getting away from the homogeneous systems and then actually starting to think about where do I want to make discrete action and only where do I want to make discrete action. But that was something done 20 years ago that has turned out to have very little traction. It produced a lot of nice papers at different engineering and physics conferences. It excited a lot of different students in architecture, but the reality of sort of like trying to get that into place has been quite difficult. And and so I have been wrestling with all of this time. I don't think I'm asking the right question. The right question apparently is not how can we do this more cheaply, more effectively, more reasonably. Apparently that was not the right question. And so I have been trying to sort of peel back and understand very much how architecture and how the field of architecture sort of deals with both technological innovations as well as sort of changes in our knowledge. Along these lines, I used to teach a course in smart materials, and I've retired that course many, many years ago, mostly because I realized that even though I was the first person to teach a course in smart materials in '96, since then those courses have proliferated, and any student out here, I'm going to guess, probably knows more about the state of art of smart materials than I do right now. But within those technologies, I'm also very much questioning the way that we deploy those technologies. And I'll just sort of run you through a quick sort of set of examples on this. If you think about the idea of automation, whether it's the Apple HomeKit, where we're dealing with locks coming on and off, the thermostats, the plugs, and so on. Many of us have certain devices like this already. Here was Google Glass. Your heat is set to 21, turn it up to 24, welcome home, unlock the front door, to the Microsoft Home of the Future. As you approach, the front lights come on and you hear a click as the door unlocks. To the Philips Home of the Future, at the front door, she is recognized by an intelligent camera, the alarm is switched off, the door unlocks and opens. To the Tron hyper-intelligent building, 1987, from the moment that the employee arrives at work, the building's distributed systems recognize him, open the doors for him. We did see a gender shift. It did go, male, female, male. To 1967, Walter Cronkite. Sorry, I apologize that for some reason some of the fonts aren't coming up very well. But I'll read this to you. Completely sealed like a space capsule with perfect lighting and temperature. When you arrive at the front door, the surveillance camera recognizes you. And, we can go all the way back to the 1920s. This is their idea of the future, that in the 1930s, the door is going to open for you. So we're now talking nearly 100 years of this sort of being this belief about what new technologies are going to bring to us. And I realize that so much of this is framing what we know in terms of framing what the future is going to be in terms of what we see, in terms of what we know, in terms of what we're familiar with. We're kind of always operating supra to our experience. And on Friday, Ann and I were actually in a symposium at Yale with Keel Mo, who talked about the fact that we design our future as if it's a colony of the present. And I thought that was a really appropriate way for thinking about that, how much of what we think about in terms of how we incorporate this type of new information, these new technologies, relates to what we know, what we see, what our experience is. So in order to move forward in this, I've been trying to sort of identify sort of key areas that we need to begin to question. And I'm going to start with a couple of these key areas. And the first one being sort of like rethinking, how we decide or how we, attribute certain types of behaviors or phenomena to certain kinds of forms. This is a building everyone recognizes. This is the Menil Collection in Houston, Texas. And this is probably one of the most famous images that comes from the monograph for this image showing how the louvers work within this building. And as somebody who specializes in heat transfer and sort of also pays a great deal of attention to how light actually moves, I would look at this image, even though this image shows up again and again and again in different types of precedent studies, I'd look at this image and said, this makes zero sense to me. It really can't work, and it shouldn't work in the location that it's at. It just makes no sense. And this is when I was just starting out as a professor at Harvard. I got a little bit of money. I went down, and what I do when I visit buildings, I always beg to be on the roof as well as beg to be in the basement. And they let me go up on the roof. And one of the things I discovered, and I need to get these images digitized. This is back in the time where I photographed everything, but with an analog camera. But I have amazing images of the roof. The roof is covered over. You know, the louvers don't work in the way that they're drawn right here. This sort of gives a little bit of an indication of it. The only place the louvers are not covered over and they are actually sort of like providing daylighting is in the lobby, the entry lobby to the building. Most of the building is actually much more like this, where the louvers are covered. Some parts of the building, they're double covered to make sure none of that sort of very aggressive sunlight, particularly with its energy, is getting into the building. Every now and then there are these tiny slits cut into the roof area that allow a little bit of washing. So this sort of idea of this whole open area where the light is coming in doesn't really happen. And yet we are so conditioned to look at the drawing, to look at the precedent, and sort of like take that precedent, sort of like immediately sort of convert it into a phenomenological response that we don't ever step back to ask how does it actually work? We just take for granted that it works in that fashion. And so this is going to take us even further to sort of another building, actually another art museum, which is dealing, which is based now not just sort of like attributing phenomena to a drawing, but in this case, sort of the types of assumptions that exist that we never question. This has to do with Louis Kahn's last art museum. He died during the construction of the Center for British Art at Yale. This, by the way, is his first art museum, the Yale Art Gallery. This is one of the great corners. The Rudolph Architecture Building is right here, one of the great corners of mid-century modernism that you see in the world taking place there. But anyway, the Center for British Art happens to be closed right now for renovation. Yale has done an amazing job in the last 10 years of going through and preserving and renovating all of these buildings. This renovation here of the first art gallery was spectacular. And so when the Center for British Art closed down for its renovation, they wanted to do what they did for the first gallery. What they did with the first gallery is they actually installed things and made changes that were never in the original building. They were a part of the design for the building, but they had been value engineered out. And they wanted to sort of maintain, veracity to Kahn's images, his desire for the building, and not so much sort of like wed themselves completely to the building that ended up. So things were installed that actually weren't in the original building, which is quite fascinating. So when they were preparing for shutting this building down, they decided they were going to fix a huge mistake that they believed had occurred during construction, and it had to do with the skylights. So the skylights in this building face south. Nobody faces skylights in art museums south. They always face them north. So they had made a decision. The skylights were going to be shifted. They were now going to face north after the renovation. But fortunately, they asked me because 2 years before the building shut down, we had a symposium at Yale called The Structure of Light, which was to celebrate the work of Richard Kelly. I'm embarrassed to say, as someone who taught lighting, I did not know who Richard Kelly was until we started working on the symposium, probably the greatest lighting designer of the 20th century. every great modernist building, Richard Kelly had his hand in. We're seeing the Seagram building over here. You know, he's responsible for why Johnson's Glass House appears the way to all of Saarinen's projects, but, you know, a remarkable lighting designer. But he was a lighting designer for all of Kahn's buildings, including the Kimball, which, by the way, also doesn't work the way that the images show that it works. And again, I've been up on the roof of that one as well. But anyway, so they saw these drawings. We were very fortunate as we were preparing for this symposium was that Richard Kelly's daughter had all of his notebooks. And she'd had all of his notebooks in the basement, so we actually had information that had never been seen by anyone other than Richard Kelly or his daughter before. And included lots of sketches about the skylight design, but there was a note, which you can't quite read on here, about how the skylight has to face south because south has less ultraviolet. And so I got a call from the Center for British Art, and they asked me to come over and say, okay, what's correct here? We have for centuries believed that skylights have to face north, particularly for anything that deals with art. Now we have this note from one person, and one person only, who says they need to face south. What was he talking about? So I went and actually gave them a little class explaining based on the way that light scatters, believe it or not, south light is way less damaging to art than north light. North light has a substantially higher percentage. Here's another image showing that. North light has a substantially higher percentage of ultraviolet radiation. If you're looking at art, ultraviolet is the worst, blue is next bad, you know, as we move our way on through. And you notice that when you go into museums and you go into textile collections, certain types of works on paper, that those rooms tend to be red because they're stripping out the green as well, and definitely the blue. But our tendency, and the reason why we tend to get this confused is that on a square foot per square foot basis, south light will have as much ultraviolet in it as north. But on a lumen per lumen basis, south light has radically less. We light by lumens, not by square foot. But when you think about a square foot of south light, you know it's got almost 10 times as much energy, sometimes much more than that, of north light. But you know, even though we might design skylighting in a spatial way, when you're designing for use, you design by lumens and not by square footage. So on a lumen by lumen value, Richard Kelly was absolutely correct, and that was designed to get the right kind of lumens, much better color, much less damaging going to the south. So they made the decision, they were uncomfortable, but they made the decision that they weren't going to switch the skylights. So a couple of years later, I'm on the board of a new Institute for the Preservation of Cultural Heritage at Yale, and they were building this massive new conservation laboratory. So here I am while it was under construction, and then while it was under construction, the new director was really excited because he wanted to show me the fact that they were going to have daylighting, and they wanted to show me the fact that they have skylights that face the proper direction, which is north. And I said, I saw you in the audience when I explained this situation about north versus south light. And his response was, I thought you were just talking about the Center for British Art. And I said, you know, I was actually talking that whole latitude around the world. That's kind of the way. And he says, you know, I'm sorry, but museums have always had everything facing north. He says, I just can't wrap my head around it. So here we are, and you can see, looking at the skylights, that blue light facing north that they have in there. And of course, they're careful not to have any of the works they're conserving on there. But to see how, you know, how rigidly they sort of had to cling to this belief system that they have, because that was what was always there, and therefore that had to be right within that. But this is also something that when it's not our particular area, and these are certain beliefs that we have out there that we tend to sort of respond to, we're also restricting our ability to appropriately use the information and the technologies that we deal with. This is one that is I've been working on for a little while, and I feel like maybe I'm close on this particular one. I've always been frustrated when it comes to how we understand thermal behavior. To this day, I cannot understand why anyone thinks we should do an energy balance around a building. We're taking a unit of property and we're doing a thermal analysis around it. That makes zero sense to me. And I've never been able to figure out what is the language in order to get us away from thinking that's an appropriate way to do an energy balance. And this is something that I'd say, this hit me a little less than a year ago. I'm putting it out there to see if this makes sense. I realize that thermal phenomena, thermal behavior, how air moves, how heat moves, those are really complex. We think they're simple, again, because our senses tell us they're simple, but those are the most complex branches of classical physics that we deal with. And if you think about classical physics, and how old classical physics is, what's interesting about heat transfer, fluid mechanics in particular, is they're the newest branches of that. And they're the last branches of classical physics to have a theoretical structure that adequately described what was going on. That nails into place in 1925. We think about our HVAC system nailed into place in 1911. That was the system that we use today. So the actual science of how air and heat move really don't, and particularly at the boundary layer level, doesn't happen until 1925. And so all of our images of how air moves really comes from a pre-theoretical understanding of the physics of it. But what we do understand well, and we understand extremely well in the field of architecture, is we understand structures. We understand a structural diagram. We understand how that structural diagram manifests itself into a diagram for a system. We understand how that system sort of appears in a building. We can go anywhere in that discourse. We can go anywhere from diagram of forces to a structural system to a building. We can go back and forth. We can enter into it at any point. We can deduce, or we can derive. We can derive a system from looking at the diagram. We can deduce what the actual diagram might be from looking at the system. It's very, very neat and very tidy. And for those of us in architecture, this is our entree into physics, comes through statics. It comes to us through a structural system that not only sort of is scaled with the building, but is actually sort of integral to the building. It's integral to the form of the building. It's integral, in most cases, to the envelope of the building. So if I put up a thermal diagram, and this is a very sort of classic thermal diagram that comes perhaps from the most classic of all textbooks on thermodynamics, it looks kind of like I could imagine this as a structural diagram. It looks as though I could take that, and if I identify, the boundaries of this, surely that maps neatly onto the form of a building. I can take my boundary, call it the envelope. I can take all the crossing. I can see the things that might be crossing there. I can imagine all of that is mapping the same way, because that's what I would do with statics. I would map statics through a structural system directly onto the building form and the envelope. I assume I can do the same thing with a thermodynamic system. And of course, we see that manifest itself in something image like this, a sort of great image from John Marston Fitch, where the envelope handles all of the force transfer that we see from our interior, which is homogeneous, to apparently that out exterior, which is assumed to be hostile for some reason, the fact that the envelope ends up being the place where everything begins to happen. And it's one of the reasons why we see things like this, sort of doubling down on the envelope, or why we see discussions like this, which I really enjoy, thinking like, well, if I'm using so much energy, then I have to make that boundary smaller in order to deal with. But if I were to come back to you and say, this has zero relationship to the formal structure of the building, but what would it really look like so that you can understand what it looks like? Well, I'll show you right now in this next image what the quintessence is of heat crossing a boundary. That is a thermodynamic system. That is heat crossing from the system to surroundings across a boundary, about as clear a thermodynamic behavior as you can imagine. There is no connection between something like this and then the form that we make on that. So let me just sort of quickly shift a little bit now. So those are some examples of where I want to challenge the way that we think about things, to sort of get us away from sort of what we observe and assuming what we observe translates into our direct understanding of something. And I'm going to share with you a couple of, actually just kind of one research project with two pieces to it that I hope go in the other direction, that if you know how something works, then you can see. So seeing doesn't necessarily translate to knowing, but knowing can translate into a different way of seeing. I'm sure many of you, I apologize again for the font not working out here, but I'm sure many of you are familiar, I hope you're familiar with this sort of great Rothko sort of debacle, but also sort of a real success story that took place at Harvard. The Rothko murals had been improperly stored, probably some of that north light coming in somewhere, but they'd been improperly stored. They had completely faded to this, right? This is what they originally looked like. They had faded to this. There was huge debate as to how they were to be restored, and a lot of concern about the fact that a restoration to the proper color was actually going to be damaging and also really impact the way that paint was distributed on these canvases. So in the end, they're only virtually restored. This is a virtual restoration in here. And to sort of show you what's going on, this is Jens Stenger, who was the conservator who did this. These are projections onto the original faded ones. So if you sort of compare back to here, this is a projection. This is untouched. This is a very, very high quality projection onto this. And here he is showing the nature of the projection. And what this requires is sort of an incredible, very sophisticated LED lighting, carefully controlled on a pixel by pixel program in order to adjust the light striking each part of there. So when you're in this room, you really honestly cannot tell that that's a projection recreating that Rothko on that damaged Rothko unless you actually interrupt the projection. So we've been thinking a lot about what Jens was doing, and as I said, I'm on the board of the Institute for the Preservation of Cultural Heritage at Yale. And so we hired him 2 years ago to see if he could bring that technology over to us. But instead of sort of thinking about necessarily the recreation or the virtual recreation of artifacts, could we use it actually to understand, not to understand our artifacts better, but to light better in spaces. So one of the things that we used him for, although he hadn't quite employed the same technique, had to do with the incredible restoration of this Velasquez, which was found in a basement in Yale, folded up and mildewed, wanting to restore that, already a heavily damaged and incredible piece of art, wanting to minimize the amount of light on this because, again, every wavelength is damaging, but using advanced LED lighting, interestingly, from the cinematography industry. Cinematography has done an incredible amount of work with LED lighting, again, both wavelength and directional control. In order to use that for the conservators need outstanding color rendition. They need great contrast control, yet at the same time you want no light on these paintings. Could we use LED lighting in order to do that? And that's what was helped in that matter. And if we just sort of think about it quickly off the top of our heads, when we think about LED lighting in buildings, we're thinking again, as Keel Mo said, as a colonizing the future with the present. We look at it as a replacement for conventional lighting. If we even think about it in relationship to what's happening in the automotive industry, and of course for me being originally a mechanical engineer, in mechanical engineering we would think of No industry is being less innovative than the automotive industry, and yet in our case, it's actually way more innovative. Here, this is all designed based on what you see, how you see, not based to provide the sort of general level of illumination that has no relevance to what you see, but all entirely based discretely on how light strikes the retina. And so there are some computational tools out there, micron scale ray tracing, which by the way was used to design that dashboard, understanding glare control as well as what field of view is going to be in the retina. And so this is part of this effort that now we're hoping to start to pull together. And yes, it's sort of sad that we're doing it in the art world, but we feel like in the art world is where we get traction. And then I'm running out of time, but I just wanted to show you this last little piece because we just hired our last person to work on this project last week. If you look at these ASHRAE classifications for art, there's 5 different classifications that tell you what the museum environment needs to be, what its relative humidity variations, what its temperature variations need to be. But if you think about it from the mind of the museum director, ideally everything would be kept in what we call a delta case, sealed up, completely, totally controlled. We're trying to break all of that apart. Yale has the 3rd largest art collection in the United States. The Collective Smithsonian's Institute are the largest. Metropolitan Museum is number 2. We're number 3 with 2 million pieces of artifacts within it, including lots of things like that. Every alum who's ever shot anything has donated to school. This amazing piece, which I'm actually going to be displaying, speaking about to the United Nations next week. First example that we have of molded plywood from the 3rd century, this sort of incredible shield that I can pick up with one finger, in this incredible totem collection to the world's largest collection of Iron Age canoes to also the world's largest collection of Baroque harpsichords. It goes on from there. But we've just sort of come together to define a way that we want to break the ASHRAE classes and actually create microenvironments for each of these objects, simple microenvironments that mitigate their movement so that these things can be flexibly curated. They can be pulled out for teaching. They can move across the country, that all of this art that actually has been hidden, locked away, sealed away, now becomes a public entity and a public good. So I just wanted to finish there, show this sort of one last slide that's one of my favorites of working with students and trying to get them to understand how phenomena actually behave. So this is a student who made a number of these headpieces with fiber optics and LEDs, trying to show and demonstrate that depth, our understanding of depth is actually not related to where a surface is. It's related to the illumination of that surface. So you can create articulation of surfaces and you can create depths simply by dealing with small micro rifts in contrast, small micro rifts in luminance. So one of these pieces appears to be about 100 feet away, one will appear to be an inch away, and they're actually all right located in this particular location. But anyway, thank you very much, and you're going to hear some great work from both Anna and Sheila, who they're inspirations to me. So.